Morning, everybody. We are excited today, and the reason why is we get to study a piece of equipment today that, one, is more complicated than most of the other types of elements, circuit elements that we've looked at so far. So that's exciting that it's more complicated. It's also exciting that it might be a little bit more useful than some of the other ones that we've seen. That's probably unfair to say that because each thing has its own use in its own place. But you're going to learn today about something called an operational amplifier, or an OpAmp, and it is a very powerful piece of circuitry that we can use to actually amplify signals. That's where it gets its name, operational amplifier. So, but by way of introduction, I wanted to talk through why we might need to amplify things and what does that mean to amplify things. And I thought a good example of this was the process of taking a signal that actually starts out encoded on a vinyl record. So if you know anything about vinyl records, basically they start off with a signal that is literally physically impressed. It's like little bumps, so to speak, in a groove on a record. And you get to see that, kind of over here. You've got this thing that's called a cartridge. That cartridge has something that's called a stylus. It calls it a diamond tip right here, but it's a little thing that sits down in the groove, and as that stylus runs across that, sort of bumpy groove that's in there, it shakes that little stylus a little bit, and by doing that, it essentially causes there to be a magnet that moves relative to a little magnetic coil. And we already talked in here a little bit about how magnetism and electric current tend to be related to each other. If you have a changing magnetic field, that tends to relate to current. And it actually works both directions, where if you drive a current a certain way, that causes a change in magnetic field. Or the other way also works, where you change the magnetic field through some physical change of some kind, in this case, this little magnet vibrating. That has a tendency to actually induce currents in the little coil over here. And then it produces some output on the leads of this little electric coil in the cartridge of this record player. Okay, now what you ultimately want to do with that signal is you want to try to hear what the music sounds like, or whatever's recorded on the record. You want to hear what that sounds like. So in order to do that, you want to take that electric signal and somehow turn that back into something physical. Right? And the way that typically works in these stereo systems is that you can drive some kind of a voltage across two leads of a speaker, and inside the speaker you have another coil. That coil is positioned relative to a magnet, and by driving current through the coil of the speaker, it causes the speaker to want to move in and out, usually fairly rapidly. And then by moving in and out, it moves air, and then you can hear what that sounded like, okay? So it goes all the way from having little bumps on a vinyl track right here, all the way to the point where it's creating these sound waves that you can then hear, okay? Now, I thought this might be an interesting thing to do in terms of some, I'll say fairly generic numbers, but I found some numbers for some of these effects on this sort of setup, so that we can kind of see why it is that we need amplification. Because if we didn't think we need amplification, it might be tempting to say, well, why don't we just hook some wires? Why don't I just hook that wire up there and that wire right there, right? We have a little electrical output coming out of this coil. It's going to send that electrical output over to the coil of the speaker. Everything should work, right? Okay. Now, I'll say it doesn't necessarily really work this way, and I'm going to show you why. So for the little electrical coil, right, that's in the cartridge, typically what comes out of that coil is a voltage level that's probably somewhere on the order of about 5 millivolts or so. Something like this. And it's, that's going to be kind of the size of the wave. So really, maybe what I should do is say, not only is it 5 millivolts, maybe it's something more like this, where we've got relative to time, some kind of a signal that might look a certain way, so I'll kind of say, what if it's a signal that looks something like that? I just made something up, but let's say that's the shape of the wave that is encoded on the track of the record, and it is creating that wave, and I'm saying, you know, somewhere on the order of about 5 millivolts or so is the size of that wave as time goes on, right? That's kind of that rough size of that wave, okay? In addition to this, I did find another thing, that it is typical that these coils will tend to feed into some piece of electronics that has somewhere on the order of about 47 is a number that I found, 47 kilo ohms. All right, so 47, think of this electrical output normally in your record player system. It's like it's going to feed into a resistor, and the size of that resistor is 47 kilo ohms. Now, technically, it's feeding into more than just a resistor, because it's feeding into some kind of a bit of circuitry that then is going to do something with that signal. But as far as it looks like to the coil feels like it is driving this resistance value of about 47 kilo ohms. So these are a couple of numbers that I found that are fairly typical for the cartridge end of this thing. Now let's look at the speaker end of the thing. This one might actually be more familiar to a lot of you, especially some of you who may do things like build stereo systems. What would be a reasonable number to say might come out of a speaker in terms of wattage, like amount of power that comes out of a speaker? Anyone have a feel for that? Okay, if you don't, I'll pick something out and say it's not unusual for a speaker to push maybe 100 watts or so. Okay, so I'm going to say, let's say this is a 100-watt speaker. All right, and let me give you another kind of parameter that is sometimes used with these speakers. Usually whatever speaker system that you're doing is designed to have a certain amount of impedance for, you know, the speaker. And what that essentially is like if you're driving that speaker with some kind of a wave, and you think of kind of the voltage of that wave, right? There's this thing that we're going to get into a little later in the course called the root mean square voltage of that wave. The impedance is something where if you take that root mean square voltage of a signal wave and divide by that impedance, it gives you about how much the current is going to be that's going to be flowing in that wire. Okay? So we can treat impedance like it's a resistance is basically the takeaway from that. And so the impedance of speakers, a common standard for what an impedance is of a speaker might be around 4 ohms or so. And for now, you can just kind of think of that as being like a resistance, right? Even though officially it's more like an impedance because it's being applied to something that is more like an AC kind of a system. Okay? So anyway, with 100 watts and 4 ohms, let me ask you this. About how many volts do you think we are going to be driving this system with? In other words, about how many volts should I be putting across the leads of this speaker if I know it's a 100-watt speaker and it's like it's equivalent to something like a 4 ohm resistance? How do you do that math? Okay. Power is equal to what? V squared over R, right? We're trying to find V. That means that V is equal to what? The square root of, okay? You multiply R times P, right? So that's 4 ohms times 100 watts. So about the square root of 400. Okay. And that gives you about what? Okay, 20 volts or so. Now, this creates the first place where you might have a little bit of concern about what we're trying to do by hooking the wires straight from the coil of the cartridge up to the speaker. We're getting how many volts out of the cartridge? 5 millivolts. And for these parameters to kind of work for this speaker, if it's a 100-watt speaker and it's about a 4 ohm impedance, that means we're probably driving it with roughly 20 volts or so. 5 thousandths of a volt to 20 volts. Okay, now here's the thing. This is what we need over here on the speaker end. We want for whatever, I'll tell you what, I'll just copy that whole thing, right? We want whatever this shape is to be what we're feeding into this speaker down here, but we want that value right there to be something like 20 volts. But the shape of the wave, we want it to be the same thing, right? So that's what we need to feed in there. This is what was getting sort of extracted out of that record player cartridge. What do you do in between to make this happen? Okay, this is kind of the big question. Before I leave this little picture right here, I want to do one other thing to kind of show you the essential problem of what we're trying to do. The essential problem what we're trying to do is actually not so directly related to things like voltage. It's actually more directly related to energy or power. How much power are we producing by this little diamond tip vibrating on this record player? Okay, we can kind of do a similar calculation to down here, right? P is equal to V squared over R. Okay, V is 5 millivolts. I'm going to put that as 0.005 volts squared over, and then that little resistance that is driving it across is 47,000 ohms. So how much power is that? Okay, let's do 0.005 squared over 47,000. 5.3, or 5.3 or so, times 10 to the minus 10 watts. Is that a lot of power? That is a tiny amount of power. It's some little tiny bit, right? But it certainly is no 100 watts that we're going to need to drive this speaker over here, right? So we need a way to sort of infuse energy, power, right, into this system and yet retain the essential shape of this wave, feeding that into the speaker. And this is only one example. There's a lot of examples of where you're going to have some kind of an electrical signal that you would like to take that signal, keep it roughly the same as it was, but then make it, more powerful in some way. Okay? Now, you might be thinking to yourself, I have seen a circuit element that can do something like this, right? And if you think back really hard, you might remember that one of the things that you may have done in the past is you had a little microcontroller, and you needed to be able to flip a relay with that microcontroller, but the microcontroller did not have enough current output to be able to flip on or off the relay. Have you ever done a task like that? What did you use in between the output of the microcontroller and the input of the relay? Okay, a lot of you might remember you used a transistor. The essential job of that transistor was to take a small current signal, right, and do what? Turn it into a bigger current signal so that you could flip on or off the input of that relay. Okay, so can we use a transistor for this? And I would say maybe kinda, right? Here's the problem. A single transistor has some characteristics to it. It does actually do current amplification. If you think about a normal, it's called a bipolar junction transistor. It does do this amplification of current, but it has some characteristics to it that are a little bit less desirable than we would want, okay? And it basically, it's a little bit hard for me to kind of get into all of why they are a little bit less than what we want in terms of how they act. But it has to do with things like how much input impedance is there, right? In other words, how much current does it take to drive its amplification of current? What's the overall limitation on how much gain you will have out of a single transistor? These kinds of things are a little bit less than what you would really want in terms of being able to do certain amplification tasks. Another thing is that there are some nonlinearities that come in for a lot of transistors whenever you start to especially if you try to drive them kind of to the limits of what they can handle. They tend to start getting nonlinear. So anyway, I'm not going to get into all the details about that, but suffice it to say that it actually would be better if we could come up with some sort of a more complicated circuit that might use several transistors and could eliminate some of those issues that you might have by trying to amplify something with a single transistor. Okay? Now, what I'm showing you with this big picture over here, you can count up a whole bunch of transistors over here. I don't know exactly how many, but it gets up to Q20 over there, so it looks like maybe roughly 20 transistors or something in this big old circuit over here. What this circuit is that you are looking at over here, this is a schematic diagram of what is inside of a circuit element called an op-amp. This is actually, not every op-amp is exactly the same inside, so this is one particular op-amp, and I don't know that I even looked up what this specific op-amp circuit it was like, or that it came from. But you can see that thing is kind of complicated, right? And I said up here, you can create a circuit like this that does a pretty good job of eliminating some of the problems that you have by amplifying something with a single transistor, but the resulting circuit is so complicated that it might be very, very difficult for someone who's a beginner. By the way, I put myself in that category with respect to this kind of thing, right? To try to build that or analyze it. It might be kind of hard to do that because it's too complicated. So what do we do about this? We would like to still be able to use a technique that we can employ for various applications to be able to amplify signals. The good news is that a lot of circuit manufacturers know that this is something that engineers need to do. Okay? So they produce what are called integrated circuits. It's a bunch of components, essentially, that they have shrunk down into a little tiny package, and they hand it all to you, and you have to believe them that inside of that little package that they hand you, it's going to behave a certain way. Okay? And so the thing that I'm showing you down here on the left side is what that package might look like. This is called an 8-pin DIP package, DIP. And inside of that package, there are actually 2 op-amps embedded into that little circuit element that you see right there, that component. Okay? Now here's the other good news. We don't have to deal with the operational amplifier model as though it is all of this circuitry over here on the right. Instead of that, what we're going to do is treat everything that's kind of in this little package right here as though it's a black box that has a much simplified characteristic to it as far as how it behaves. We can define some inputs. We can say for those inputs, here's how it's going to behave on the outputs. And we can do that in a much more simplified way without having to try to accurately model all of the little different components that are inside of the circuit. Does that make sense? So those are kind of the 2 elements that we use to sort of get around having to do all the complicated stuff. First, other people have incorporated that into an integrated circuit, so that's great. And then we can analyze that using some relatively simple rules, and that's what I'm going to get into next. Okay? With me so far? All right. So here is 2 kind of categories that I'm going to talk about here a little bit. Neither of these is exactly what is physically inside of an op-amp. But both of these are ways that we can treat all that stuff in the op-amp, in terms of the mathematics of it, to model it. Neither of these is actually perfectly accurate. Okay? So the one that's on the left, this is a relatively common style of a model that tries to take into consideration some of the practical considerations that would have to happen in a real op-amp that would try to kind of model its behavior that would be less than ideal. Okay? So that's what's on the left. And on the right is the picture that we normally use to talk about op-amps. We don't usually try to show anything that's inside of the op-amp. We just define a few rules on what that op-amp does. So the one that's on the right, I kind of consider that to be an ideal op-amp, whereas the one that's on the left, we're talking about something that has some parameters you can use to try to describe its behavior and get closer to what a real op-amp might do. Just to maybe help comfort you a little bit, even though I'm talking over here about non-ideal op-amps versus ideal ones, we're really only going to work with the ideal ones. I'm just trying to express some of the characteristics of the ideal op-amp with the idea in mind that there are some other things that might make it less than ideal. Okay? So let's talk about these. On the left, what you see here is basically a rendition of what is sort of you can model as being inside of an op-amp with respect to what it looks like from the outside, right? So in other words, if you look into these terminals on the left, what it might look like is that you essentially have some kind of a resistor between those terminals, and it might let a certain amount of current through based on that resistance if you put a voltage across there, right? It also, you might see in here, has this little dependent voltage source that gets multiplied by, whatever that input voltage is over there. It's going to multiply that by some multiplier to create some voltage with this dependent voltage source, and then feed that through some kind of it's called an output impedance, right, R out, before it goes out to some output voltage. Okay? Now, when they make one of these op-amps, what they are always trying to do is they're trying to do a few things on here that I'm going to talk through them on these bullets, right? First of all, you have a better op-amp the larger you can make this Rin, right? So if you're an op-amp manufacturer and you would like to tout your op-amp relative to others, you say, look how big my Rin is, right? They sometimes call that an input impedance, right? And if that is really, really high, what that means is that you can put voltages across these two terminals and it will cost very much more little energy, right? In other words, if you can make an infinite resistance right there, then no energy will flow into and out of the input terminals, right? In other words, you can excite this circuit with no input energy, right? Because power is voltage times current. If you increase R really high, that will eliminate current, and so you can essentially excite this circuit without any power. Isn't that cool? So that's what they're going for, is to try to make that R value as high as possible, Rin. Now, can they make it fully infinite? Okay, that's hard to do with anything in the real world, right? But they're trying to make that Rin value as high as possible. Okay. Second characteristic that they're all trying to do is they're trying to make this G factor right here as large as possible. All right? Meaning that if you put any voltage across these input terminals at all, it's going to try to amplify that voltage as infinitely as possible. Now again, that has its limitations. You can't physically do that in the real world, but the larger that G is, the better your op-amp is. Okay? Now this is a point where a lot of people might balk at that idea and saying, well, how do you know how much gain we need out of our op-amp circuit, right? In the case of the record player I talked about first, you didn't need infinite gain. You needed a lot of gain. You needed to take that tiny 5 millivolt voltage and turn it into a 20 volt voltage. That's not infinite. It's large, but it's not infinite. I'm going to show you here in a little while that you are going to be able to make any kind of a gain that you want to if you presume that you can make a circuit element like this where G is just as large as possible. Okay, so that's kind of a preview of what's coming up with that. Lastly, R out being as small as possible. So the reason that R out is included in this kind of real behavior model is that real op-amps typically have a hard time holding whatever voltage they were supposed to be putting out if you demand that they also put out a lot of current at that voltage, right? The more current you demand out of it, then that usually has an effect of causing the voltage to fall a little bit, right? And that's because inside of here, it's very difficult to produce something that is truly an ideal voltage source It usually behaves much closer to something like a practical voltage source, right? But you're better off if R out is smaller, not larger, right? So your real op-amp tends to have these characteristics, and if each one of those trends the direction I've identified in those bullets down there, you start to approach an ideal op-amp. Does that make sense? So now let's talk about the ideal op-amp. For one thing, I think I mentioned this, but you don't usually ever draw any of this stuff inside of an op-amp. You just draw a little triangle. You show your two different inputs. The one that is labeled plus is called a non-inverting input. Let me tell you what this doesn't mean. The fact that I've labeled it plus does not mean that it has to have a positive voltage on it. Okay? So we have to dispel that maybe misconception right at the very beginning. Right? The plus and minus are really only there to label that one of your inputs is an inverting, the one that's negative is inverting, and the one that is positive is a non-inverting. Okay? What that means is that if you were to increase the amount of voltage on the negative terminal, that will have the effect of decreasing the output voltage. If you increase the voltage on the plus one, that's going to have the effect of increasing the voltage on the output. That's what that means, okay? So don't get confused with those labels. That's just so that you know which one is an inverting input and which one is a non-inverting input, okay? And what I'm going to do down here is talk through these rules that we're going to use for ideal op-amps and being able to analyze them. Okay, first of all, we are going to pretend like it is possible to get an infinite impedance, that is resistance, internally at the input terminals, at both of the input terminals. So essentially, it's like Rin is going infinite, and if we do that, how much current can flow on the input terminals? Okay? If I draw this right here, if I talk about currents on either of the input terminals, okay, I has to be 0 on both of these if that has infinite impedance on the inputs, right? No matter how much voltage you put across them, it's going to allow 0 current to flow in if you assume that it's got infinite impedance. Okay? So that means 0 current happens on both of the input terminals. You comfortable with that? Okay? Next, we're going to pretend like there is an infinite gain for the dependent voltage source. That's the little G parameter over here. If a circuit is set up to be stable in its operation, okay, that means it kind of matters a little bit what kind of circuitry I hook up to this op-amp. But if you hook up a circuit that allows this thing to be stable, by assuming you have infinite gain on the dependent voltage source, that is going to mean that you must have 0 volts across the input terminals. Or else what? What if you had a non-zero voltage across the input terminals and an infinite gain? How much output would you have? You'd have to have an infinite output, right? If you have some non-zero voltage you put across these terminals, that would be a non-zero Vin on the model over here, right? If you have a non-zero value there and an infinite G, then that means you're going to generate an infinite voltage on the output, okay? And that can't happen. So what it does is actually the rest of the circuitry that I mentioned there that you're going to hook up to this op-amp, it is going to help to balance that and essentially try to make the two input terminals reach 0 volts across them. That's functionally what happens with one of these op-amp circuits. It's going to react by trying to put those two voltages equal to each other. Okay? So that's the first two rules. The next rule is there's no limit to how much current, voltage, or power your op-amp can source. In other words, we don't care what you hook up to the output. It's going to be able to produce enough voltage and enough current to behave like it's going to behave, and there's no limits. Okay? Now, that one is obviously something that doesn't really happen in the real world, but we can set up limits within which that behavior will happen, right? You can kind of set up your op-amp so that you don't reach the limits of how much voltage or current or power they can source, okay? And then lastly, the last rule that we're going to have down here is that stable behavior depends on feedback. That's the rest of the circuit that might be hooked up to the op-amp. It depends on feedback from that circuit coming back into the input terminals. And there's a specific way you've got to do that in order to make your op-amp stable. It specifically has to, whatever output voltage you have has to go through circuitry and eventually get hooked to the inverting input, okay? The reason for this is that what happens with your output is some change might occur, the output increases. You don't want that to then feed back into the non-inverting input because that's going to make the output increase more, right? So you really want to have feedback to where it connects up into the inverting input, because that means if you have some kind of a change and you have an increase in your output, it's going to have the effect of actually decreasing the output once the feedback loop executes. Okay? Now that's a little bit out there. Let me give you a little bit of maybe some comfort with this. As far as the problems that y'all are going to work in this class, only 2 of these rules really matter to you. The first 2. These 2 rules, 1 and 2, okay? Those are the only rules you're really going to use, okay? When it comes to the other rules on here, one way I like to put it is, if I'm the one giving you problems to work in this class, those 2 rules are my job to kind of think about, right? I have to give you a circuit that is going to be stable, right? I have to give you a circuit where maybe it's even realistic that it could produce a certain amount of power or something like that, but it's not going to have an impact on your ability to analyze those circuits, okay? So the first 2 rules, even though we've talked about these sort of 4 rules that we can kind of think about for ideal op-amps, really it's only the first 2 that are going to matter to you when it comes to actually working one of these problems. All right, before I move on too much further, any questions? Yes, sir. VS plus, VS minus. Good question. I'm glad you brought that up. He is looking at this model over here, okay, the one that says closer to real behavior, and it looks like you're basically looking at these 2 values right here, VS plus and VS minus, okay? Those terminals right there are an acknowledgement that in order for this op-amp circuit to work, it has to get energy from somewhere. Right? Whenever you make one of these op-amp circuits, like if you build one on a breadboard or whatever, your op-amp circuit actually has to get some sort of source power from somewhere, right? And that power doesn't have to be anything complicated. All it needs to be is some voltage that's high enough so that it can drive your output voltage to where it needs to be, or some input voltage over here, VS minus, that is low enough that it can drive your output voltage as low as that needs to be, right? They sometimes call these rails, right? And if you have your VS plus and your VS minus, that's sometimes called the rail-to-rail voltage, right? That's like you're supplying it with energy. The energy is nothing like fancy or complicated. It's just some sort of source voltage that's available that can pump current into this thing at that voltage to supply power, right? But it's a good question. I actually meant to talk about those, and I'm glad you asked that question because I neglected to mention the VS plus and VS minus, okay? Y'all are going to do a lab here before too long, and you're going to actually get to build one of these circuits, and for that circuit, you're going to have to hook up your VS plus, your VS minus, in order for your op-amp to behave like it's supposed to, okay? Now, there's not much interesting about those terminals other than you have to supply energy at a positive voltage and as a negative voltage as well, okay? Good question. Other questions? All right, let's do a quick example using the rules that we just learned, okay? Now, in this example, you can assume that the op-amp that I put in this example is ideal, right? And that's going to be the case for all of the different problems that we work. It says very simply in the problem statement, find V out for this circuit. and it identifies V out down here as being the voltage across those two terminals. Okay? And we need to use our rules in order to come up with what the output voltage is for this circuit. All right? Where would you like to start? Okay, let's go back and remind ourselves of the rules now that we have a circuit in mind that we're going to try to apply them to. Okay, first rule is 0 current on input terminals. Rule 2 is 0 voltage across input terminals. Okay, how do we apply that to this circuit? How about if I just label these real quick on there? 0 current on my input terminals. So what that means is if I think of current on this little leg right here, 0 amps. Right? And on this little leg right here, 0 amps. No current is flowing on either of those two terminals into and out of this op-amp. Okay? All right, now, before I get into kind of the rest of it, let me propose something. When I look at this circuit, it looks to me like using a nodal analysis might be a nice way to do this problem. Okay? And because I'm thinking about doing a nodal analysis, what I'd like to do is go ahead and highlight some nodes. Right? So let's say that down here, let's me call this my, my ground node. All right? Let me call this my output node up here, right? I don't need to actually call it anything particular, but that is a node where I have my output, right? Where else might I have a node? Okay, I have a node right here. With me so far? Let me put another node over here. Okay, let me get one more node that I identify right here. Okay, now I guess technically if I wanted to, I could do even another node, pick another color here, and say there's another node that I could have right there. Okay? Why does this help me? Or maybe it doesn't, but let's kind of say, why do you think this might help me to identify all my nodes? We're going to do a nodal analysis. What do you typically do after you identify your ground node? Okay? Before equations, we probably want to identify some actual voltage variables, right? So let me actually say that my yellow node over here, I already have a voltage defined for that yellow node relative to ground. So instead of defining another variable, let me just use V out for that one. Okay? So let me define some other ones. What if I call this V1 for that little aqua-colored node up there? Let me call this one V2 for that purplish-colored one up there. Now's the time for us to get back into our rules for op-amps. If I identify V1 for the aqua-colored node up here, what is the voltage that's attached here to my inverting input, right? What's the voltage for my non-inverting input? What does Rule 2 say? 0 voltage across input terminals. What that tells me is that if V1 is the voltage on my inverting input, V1 had also better be the voltage on my non-inverting input. That's one of my two rules, right? That we've got to have 0 voltage across those two input terminals. Okay? With me? Now I have to do one other thing here too. How much current flows through the 1 ohm resistor right there? None, because there's no place for it to go because it hits an infinite impedance when it hits that input, right? If there's 0 current flowing across my 1 ohm resistor, how much voltage do I have across my 1 ohm resistor? 0. And if I have 0 volts across my 1 ohm resistor, how much voltage do I have on my orange node? Okay, not 0 necessarily, but it has to be the same as the other side of the resistor. So I basically said V1 has to be the voltage for the aqua-colored node. V1 also has to be the voltage for this little light purple one down here. And V1 has to be the voltage for the orange one as well, because 0 current flowed on that 1 ohm resistor right there. Okay, so far so good? Now, this actually simplifies our process of trying to work this nodal analysis problem a good bit, right? Let's actually start working this to see what it looks like. I'm going to start with an analysis of the aqua-colored node, okay? And let's think about all the currents that are exiting the aqua-colored node in a nodal equation, okay? How do we do that? Okay, we'll start with V1 minus V out over what? 4 ohms. Then let's go to how much current, well, let's talk about this one. How much current leaves on this little leg that goes down into the op-amp, into that? Yeah, we said 0 amps down that way because you have infinite impedance right there. So we don't have to worry about that. How much current leaves the node going from aqua toward purple? Okay, over 2 ohms. Okay, and is there any other place where current can go? Or not? Looks like that's it for that node, since none of it can go into that inverting input of the op-amp. That's it. Okay? Now, what equation would you like to write next? How about the one up there for the purple, right? I heard someone say V2, right? So for this purple node up here, we'll write a little nodal equation up there as well. What we have there is we have 3 amps entering. How do I count that? Negative 3 amps plus, then I have V2 going down to V1 from the purple down to the orange, right? So V2 minus V1 flowing across a 5 ohm resistor. Then what? V2 minus V1, oddly enough, again, right? Flowing across a 2 ohm resistor. All right? Any other places where I can have current coming in or out of that node? Okay? Talking about the purple node, I dealt with the 3 amps, I dealt with the 5 ohm resistor, and I dealt with the 2 ohm resistor. So that's it for that node. Okay? Now, is this solvable yet? I've got 2 equations. How many unknowns? 3. So that kind of creates a little bit of an issue for me, that I've got 2 equations and 3 unknowns. But do I have any more equations I can write? Okay. The next one that might be kind of interesting here is the orange one, right? So what do I write there? V1 minus V2, I hear someone say, over 5 ohms. That's how much is exiting from the orange going up toward the purple. How much exits going from the orange over toward the light purple over here to the, okay, again, 0 because it's not allowed to go into that input, so we don't count anything there. Then we have V1 going down to the ground node, right? So that's going to be V1 over 6 ohms. And I think that's it for that node. All right? Does that help us out? Certainly does, right? That means that we have everything that we need here. That's a system of 3 equations and 3 unknowns. Okay? And that means we can solve for what we are missing. You want to see what those results end up being? V1 ends up being 5.143 volts. V2 is 9.429 volts. And V out has to be negative 3.429 volts. Okay, and so that last one that I just wrote, that is the answer to the question that was asked. Okay. If you want to, you can actually go in and check some things, right? If you look, there's two different places where we really only have two places that flow in and out, right? The aqua-colored node up on top, you really only have one place to enter and one place to exit, let's say, right? And the orange one is the same way. There's really only two entry-exit points for the orange one as well. Would you like to see if our, does it make sense for these values to be like they are for those two? So what that would look like is if we did, let's say, V1 minus V out, which would be 5.143 volts minus a minus 3.429 volts over 4 ohms, okay, how much current would that give us? Anyone have that? Okay, I'll do it real quick. 5.143 minus, well, plus really, right? Plus 3.429 over 4. That gives me 2.143 amps. Now, what if I take V2, 9.429 volts, minus V1, 5.143 volts, and divide that by 2 ohms. Okay, that should give me what? We can check and see whether or not it does, but it should give me, did I? Okay, so we're assuming here that current flowed this way from V1 to V out. And in this one, I'm assuming current flows the same way because we can't have any current flowing down here. So that's, I think, there was some concern that I did the voltages backwards, and I can see that, but I did them that way actually on purpose so that I could get these two currents to flow the same direction so we'd end up with the same number. Okay? Good catch on that anyway. All right, so we have 9.429 minus 5.143 over 2 ohms, 2.143 amps. And I'll tell you what, I don't think I need to do that again, but we could do a very similar kind of a thing for the orange node and see whether or not we had the same amount of current flowing from V2 to V1 as from V1 to ground. Okay? All right, so I think that's where I'm going to stop for this lecture for right now, and we'll probably pick back up. The next one that I do, I'm going to show you a few commonly used OpAmp circuits that do particular tasks. So that's going to be the next lecture that we have. Fair enough? All right.